Okay, today we're going to talk about the centripetal force. Now, recently we talked about the centripetal acceleration, okay? We know forces, a net force will cause an object to accelerate. So if we have a centripetal acceleration, there's got to be a force causing this acceleration, okay? Going back to Newton's second law, force equals mass times acceleration, we are going to use the equation that if I have a centripetal force, if I have a centripetal acceleration, then it must be caused by a net force, which we're going to call the centripetal force. Okay? Now, another thing that we know is that the direction of the centripetal acceleration is going to be the same as the direction of the centripetal force, because the acceleration and the force always point in the same direction. So, the centripetal acceleration points towards the center of a circle. So therefore, the centripetal force is also going to be directed towards the center of the circle. The other thing we said is that when there is an acceleration, there needs to be a net force acting on the object. So this centripetal force is actually the net force acting on the object. And you can remember we wrote net force with the Greek letter sigma in the past. So the net force is our centripetal force. Let's go ahead and talk a little bit more about what this means. Okay, just to kind of recap, centripetal force is a force that maintains circular motion, okay? It's got a centripetal acceleration. It's because it's changing its direction, okay, caused by a centripetal force. It is a vector. It has a magnitude and a direction. The direction is towards the center, okay? Centripetal, center seeking. The symbol is the F, because we always use F for a force, and with the subscript C for centripetal. The units. In this class, we will use newtons, okay? Now, there might be some engineers and people in the United States who use pounds, but for the sake of our class, we are going to use newtons. The equation we just looked at, it's a lot like Newton's second law, except we're using a centripetal acceleration, so it's the centripetal force. And we also just talked about how the centripetal force is the net force acting on an object. So let's go ahead and look a little closer at this. So let's say here we have Earth, okay? And we know the moon orbits the Earth. So there's the moon orbiting Earth. Okay? Well, the centripetal force is the force that's keeping the moon orbiting Earth. In this case, the centripetal force is the gravitational force, because the gravitational force is what is keeping the moon in orbit. Okay? Another example. Okay, let's say that you're playing tetherball and the rope breaks, okay? And you decide to take that rope, okay? And the tetherball's on the end of it, okay? And you're going to swing that around your head just in a circle for fun, okay? So what is keeping this tether ball going around in a circle above your head, okay? Well, if it wasn't attached to the rope, it wouldn't be going around in a circle above your head. So in this case, there is a tension force, and that tension force is what's keeping the tether ball going in a circle. So the tension force is the centripetal force. But didn't we just say the centripetal force was the net force? Okay, well, let's look at another example. Here we have somebody going around a circular track on a bike, okay? What force is keeping the person from skidding off to the side? Well, imagine that right here there's, a pile of gravel, okay? And maybe you've been on a bike and you're going really, really fast and you hit gravel, okay? And then you slide off. It's not a pleasant experience, but maybe it's happened. Okay? Well, you slid off because there wasn't friction anymore when you hit this gravel. So in this case, the centripetal force is the frictional force. But you might be saying, hey, there's more forces on this person than just the frictional force, and the centripetal force is the net force. Well, let's take a look at that. Okay, let's put our bicyclist right here. Okay? The forces that would be acting on our bicyclist would be the gravitational force acting straight down, the normal force provided by the ground acting straight up, and then there would be a frictional force acting inward. Well, the normal force and the gravitational force are going to cancel each other out because the person is not accelerating in the y direction. So these two cancel out, which means the frictional force is the net force, and the frictional force is the centripetal force.